Welcome back everyone to section number 1. This is our second video, and here we're talking about the applications, right? Why do you want to calculate out area under a curve? And the claim is, well, we saw actually in the motivational video that anytime that you have a function that represents a rate of change, if you want total change, that's somehow, right, that has something to do with area under the curve. So in this video, we're going to break it down a little bit more, and we're going to try to argue that the area under the curve, if we have a velocity function, right? So this is a rate of change of position, right? Velocity is rate of change of position, that this will yield displacement, again, total change. And then we're going to solve a couple application problems. So again, you may have learned from your physics class or your favorite math class from before that distance is equal to rate times time. So something like this, and this works when you have a constant rate. So again, constant rate, think velocity when I say rate, but it can be other things as well. All right, so let's go ahead and solve this example right here. Suppose a runner travels at 20 feet per second. So this is a specific rate, a rate of change for the position. So in this case, I'm going to say just r of t, and notice that this is not changing with time, that this is a constant 20. So constant 20 feet per second. How far does she travel between t equals 1 second to t equals 9 seconds? So in total, she's traveling 8 seconds, right? So in this case, if you want the distance, this is going to be equal to the rate, 20 feet per second, times the number of seconds that she was running for. So in this case, times 8 seconds. And so we can see that the seconds in the numerator and the seconds in the denominator, right, these perfectly cancel out, and we're left with 160 feet. So this is how you may have solved these problems before. Now I'd like to think of this in terms of the graph, right? Think of this graphically. So if I go ahead and graph my r of t function here, maybe at a height of 20. So here is my r of t function, not a great straight line, but okay, something like this. And we're traveling at this 20 feet per second between t equals 1 and t equals 9. So maybe here's 1 and here is 9. Again, this has units of seconds. This 20 has units of feet per second. Let me go ahead and rewrite that. Okay. And so if you were to calculate out the area under this function between t equals 1 and t equals 9, you can see that you're making a nice rectangle here. Nice rectangle between t equals 1 and t equals 9. And if you were to calculate out the area of this rectangle, again, we would have the width here would be 8 seconds, and the height here would be 20 feet per second. And so the area altogether, well, you would multiply these and you would get 160, and feet per second times second, right? The seconds would cancel and you would get 160 feet. And so now hopefully we can clearly see that actually the distance, or well, more accurately displacement, is the area under the velocity graph, right? Again, velocity is the rate of change for displacement, or for position, I guess. And the way we want to be able to extend this to more realistic situations, right? Because it's kind of maybe unrealistic for someone to always travel at the same speed, right? This constant rate is kind of hindering, right? Often the rate of change, the velocity, it changes, right? So let's go ahead and think about this example right here. So we have a more complicated velocity function, or a more complicated rate of change function right here. And I would like to approximate or try to figure out how far this runner is traveling between t equals 1 and t equals 9 seconds. So just as before, well, I can go ahead and maybe block off from t equals 1 to t equals 9. And if I want to know how far, right, what was the displacement of this runner, the distance that she traveled, well, that's going to be the area under this curve. But now this time, it's not going to be just a nice rectangle. Right? We have some more complicated shape here. And in fact, I don't know an area formula for this more complicated shape, right? It has some like curvature to it, but it doesn't look quite circular. So I don't know what the area formula for this is. And so as we were doing in our previous video, the idea here is that we're going to approximate it for right now, and then later on we're going to use calculus to actually, formally evaluate this out here in section number 2 of chapter 4. So let's go ahead and approximate. How far she traveled between t equals 1 and t equals 9 using left-hand sums and 4 rectangles. So I have from 1 to 9, and I need to break this up into 4 rectangles. So let's see, here's maybe 2 rectangles right here, and then let's split those in half again. So here we now have 4 rectangles. So each one, notice that the width of each one of these rectangles is 2. So if you'd like to, you can say that delta x, or delta t really more accurately here since this is t value, so delta t is equal to 2. So that's the width of each one of these rectangles. And then we need to choose heights, and in this case we're going to use a left-hand sum. So for our first rectangle, I'm going to use this left-hand point right here, so this is the height that we're going to choose. And for my second rectangle, I'm going to use this left-hand point. And for my third rectangle, I'm going to use the left-hand point. And for my fourth rectangle, I'm going to use the left-hand point. And there we go. So one of the things that we wanted to do was sketch the area on the graph above. So let's go ahead and shade this in. This now orange area is going to be our approximation using 4 rectangles and a left-hand sum. And so now let's go ahead and calculate out what this is. So the width in each case is going to be 2. So maybe for my first rectangle, the width is 2 and the height is 6. And let me be really explicit about my units here. So my width here is 2 seconds. And my height is going to be 6. And this is going to be feet per second. My second rectangle maybe has, again, a width of 2 seconds, right? This always stays the same. But now the height is 5 feet per second. And now my third rectangle, again, a width of 2 and a height of, again, it looks kind of like 5 feet per second. And then finally, I'll start a new line down here, plus another 2 seconds times 6 feet per second. And so again, we see that there's a lot of cancellation here, right? All of these seconds kind of cancel out. And so I'm going to have 12 feet plus 10 feet plus 10 feet plus 12 feet. So in total we have 44 feet. So how far did she travel? Well, approximately 44 feet. She traveled approximately 12 feet in the first 2 seconds, 10 feet in the second 2 seconds, 10 feet in the third 2 seconds, and then another 12 feet in the fourth 2 seconds. If that makes any sense. All right, so I really like this example because it helps us visualize, right, what we are doing. Right, with a graph we can really visualize. We will not always have that luxury though. So in this final example that I have for us, I'm just giving us an equation, right? So velocity of a runner is given by root t meters per second, and I'd like to approximate the distance the runner traveled between t equals 0 and t equals 4. And again, this is going to be an approximation. This is actually, if we sketch this out, it's not a nice geometric shape, so I don't know an area formula for it, right? It's not going to be a triangle or a rectangle or anything nice, not even a circle or anything. So we're going to approximate this. We're going to approximate it using time intervals of 1 second and a left-hand sum. And then we're going to go ahead and use time intervals of 1 second and a right-hand sum. Get a couple of approximations here. All right, so again, let's solve this problem. Notice that we don't have a graph. In this case, right, the function's actually simple enough that we could graph it, right, by hand. But I want to get into kind of the habit, if the function is too complicated, right, we won't even be able to graph it. And so the way that you would solve these problems is by making a table. Right? So again, the runner traveled from 0 to 4 seconds, and we're going to use 1 second intervals. So I'm going to start at 0 and end at 4, and I'm going to do 1 second intervals. Right? So 0 to 1, 1 to 2, 2 to 3, and these are all t values, right? So t values, and then I want to know what is the velocity in each one of these cases, making my table here. So if I wanted v values, right, so for velocity here, if I was to plug in 0 into our velocity, right, we would get out 0. If I was to plug in 1, well, the square root of 1 is 1. The square root of 2 is nothing nice, right? It's just the square root of 2, no way to simplify that. The square root of 3 is just the square root of 3, and the square root of 4 is going to be, well, 2. That one actually has a nice evaluation. Okay, so now that we have this table, we can go ahead and solve the problem. So using time intervals of 1 second and a left-hand sum. So 1 second, that's going to be our delta x, or really, I guess, our delta t in this case, right? That's our time intervals, and that's how we kind of split this up. And so, okay, the total distance traveled, so if I want distance maybe, this is going to be equal to, let's see, 1 second. That's going to be the width of the first rectangle. Again, kind of think of this, here's our first rectangle, here's our second rectangle, here's our third, and here's our fourth. So for our first rectangle, right, we have the choices between 0 and 1, and we're going to use the left-hand sum. So I'm going to always choose the one on the left, so that is 0 in this case. So again, between 0 and 1, I'm choosing the left-hand sum. So that's going to be 0, and this has units of meters per second. Meters per second. Our second rectangle, right, again, the width is going to be 1 second, again, specified over here. And the height, we have the choice between 1 and root 2. We're always choosing the left. So in this case, 1 meter per second, plus width again, 1 second, times, again, the left-hand sum. So we're going to choose the left-hand endpoint here. This is root 2 meters per second. And then finally, 1 second. Again, that's the width and the height. On our fourth rectangle, we're going to choose the left-hand sum, so that's going to be root 3 meters per second. Again, we can see that there's lots of cancellation here. Seconds and seconds, seconds and seconds, seconds and seconds. There we are. And so we're going to have, let's see, 0 meters plus 1 meter plus root 2 meters plus root 3 meters. And so in total we have, let's see, 1 plus root 2 plus root 3 meters. And that is our final answer. Of course, we could plug this into our calculator if we got a calculator, but on quizzes, exams, heck, even our homework, right, we can enter the answer like this and we get full credit. All right, last part here, I went ahead and copied our table down just so I don't have to keep on jumping back and forth. But using the time intervals of 1 second and a right-hand sum, again, I want to go ahead and approximate the distance that this runner traveled. So again, this 1 second right here, this time intervals of 1 second, right, this is telling you the width of your rectangle, right? So this is your delta t, this is 1 second. So again, that's why you split this up from 0 to 4 in intervals of 1 second. 0 to 1, 1 to 2, 2 to 3, 3 to 4, and this gave us a total of 4 rectangles. So we're going to calculate out the area of each one of these rectangles, but now we're going to use the right-hand sum. So again, distance. And notice that because each one of the widths is always 1 second, I can factor this out, right? And I can have 1 second times, and now I'm just going to go ahead and sum together the velocities. So it's similar to back here. If I just factored out this 1 second from each one of these pieces and then summed it all together, this would have yielded the same result. So I'm going to show you a little bit faster way to do this problem. Okay, so 1 second times, and now the right-hand sum, so we're going to choose the right-hand endpoint here, so this is going to be 1, so 1 meters per second, plus, okay, on my second rectangle, I'm going to choose root 2, so this is going to be root 2 meters per second. In my third rectangle, again, I get to choose between root 2 and root 3, I'm going to choose the right-hand endpoint, because it tells me to, so root 3 meters per second. And then finally, on our fourth rectangle, I get to choose 2 meters per second. And so when I add these all together, I have 1 second times, let's see, 1 plus 2 is going to be 3 plus root 2 plus root 3. And notice that all of these have meters per second. So I'm kind of factoring out meters per second in this case. And so the seconds here cancel with the seconds here. And 1 times anything is just that anything, right? And so we have 3 plus root 2 plus root 3 meters. So this is using a right-hand sum. Notice that we get a different answer here. 3 plus root 2 plus root 3. And again, without a calculator, there's not really much more that we can do. We just go ahead and enter our answer like this. All right, that's it for section number 1. Next time when we talk about section number 2, we're going to be talking about how can we do better approximations, right? So these are approximations, but if we wanted better approximations, how would we go about that? All right, I'll see you then.